This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you. Back before the combination of ideal gas law particles in a box, and back before that box was called a black body, the scientists working with the gas laws wanted a way to know what was happening inside the box without opening it and ruining the experiment. In 1860, Maxwell formulated his distribution of molecular velocities by, quote, demonstrating the laws of motion of an indefinite number of small, hard, and perfectly elastic spheres acting on one another only during impact. Instead of saying that the particles are hard, spherical, and elastic, we may, if we please, say that the particles are centers of force, of which the action is insensible, except to a small distance, when it suddenly appears as a repulsive force of very great intensity. End quote. Thus Maxwell was imagining a box full of quantum particles, or as atoms, and imagining how we would measure all of these velocities. In 1871, the physicist Ludwig Boltzmann generalizes Maxwell's distribution of molecular velocities, creating the Maxwell-Boltzmann distribution. This statistical distribution describes the probability of finding particles with certain speeds inside of a closed, stationary container. Given the notion that you could track a molecule as it bounced around the box, you could find a method of tracking all the particles in the box, and therefore you would not just be able to predict the speed of a randomly selected particle from somewhere in the box, but you should be able to find every particle in the box, which is currently at a certain energy level, and that you can find the number of particles for each energy level possible to the box, which is called the Maxwell-Boltzmann statistics. The major question of concern here is how many energy levels are possible for the box. In 1879, Joseph Stefan was thinking about Kirchhoff's black body radiation. If you have a box with a small pinhole in it, light will get in. But the box is designed as such that that light bounces around and gets trapped inside, and the light loses energy to the walls of the box. And the only radiation that can escape the pinhole are the radiant heat energies from the walls which point towards the hole when first emitted. Therefore, the temperature of the box can be found by measuring the temperature of the pinhole, as if the hole itself was a surface. Stefan observed that the total energy which radiated from that surface over time was directly proportional to the black body's temperature to the fourth power, aka the amount of energy radiating from the surface area over time depends on the temperature of the black body, specifically depending on the fourth power of the temperature. The higher the temperature, the more energy to radiate away. If you treat the sun as a black body, as it is one, the energy radiated from it is not reflected but emitted, and the surface area of the sun being roughly known, and inferring from past data, that the energy flux of the sun was about 30 times greater than that of known lab experiments at the time. And from his law, Stefan calculated that the surface of the sun is approximately 5,300 degrees to 5,838 degrees Celsius. All in all, pretty simple and mostly uncontroversial. More temperature, more energy flux. Higher energy flux predicts finding a higher temperature. The higher you go toward infinity in temperature, the higher you go toward infinity in energy flux. In 1884, Boltzmann derives the Stefan-Boltzmann black body radiant flux law using Stefan's law, and providing a connection between particles moving, temperature, and radiant emittance. In 1896, Wien takes the fact that the sun's light can be divided into wavelengths of light, and restated them as the wavelengths of black body radiation, and combines that with Maxwell-Boltzmann energy distributions for atoms, which are the energies of the particles from the Maxwell-Boltzmann statistics. Wien is therefore able to convert the temperature mapping to the spectral wavelengths of light, and can predict the color of black bodies given their temperatures, which are associated with how many particles there are, how massive they are, the volume of the container, and the pressure of the container. For example, if you take a dull gray metal and you blowtorch it, as the temperature increases, the color of the metal goes from reflecting light to emitting light, starting from red to orange to yellow to white. If we keep going, it would become invisible to us, and would start emitting ultraviolet, then X-ray, then gamma rays, very tiny wavelengths of light. For example, according to Wien's law, the peak wavelengths of a human body is the constant 2,898 micrometers, kelvins, divided by the body temperature in Kelvin. Say that the human body is around 300 Kelvin, then the peak wavelength that we emit would be about 10 micrometers, or about the size of infrared radiation, which is true. And for the sun, the temperature was about 7,500 Kelvin. So we get a peak of about 0.5 micrometers, which gets us a peak around the green region of the visible light spectra, which again is true. However, we see white, as green is in the center of the visible spectrum, which means that our eyes receive all of the visual colors in about equal amounts, which is white to us. Then the sunlight, which has slightly more green than the rest, hits the air in the atmosphere, and the blue wavelengths are more easily scattered into the air, whereas the red and green pass right through, thus making the sun itself look yellow in a blue sky. The man that discovered that blue light was being scattered into the sky was John William Strutt, 3rd Baron Rayleigh, or Lord Rayleigh for short, Rayleigh for even shorter. The phenomena of why the sky is blue was called Rayleigh scattering. Rayleigh was responsible for solving many, many problems in physics, one of which he received a Nobel Prize for. But he is far more famous for the one problem he turned from a problem into a catastrophe. Historically, however, this is a giant lie. The ultraviolet catastrophe was coined as a term 11 years after the solution was already posted. Planck solved the problem before Rayleigh could even break anything. The history that states the ultraviolet catastrophe is a problem was created more by Sir James Jean, who believed in the luminiferous ether, and was the only one concerned about this mismatch between classical electrodynamics and Planck's quanta, and when his results failed, he blamed the ether for being at the wrong temperature. Or more accurately, claiming that the matter and the ether were not in thermal equilibrium. Jean also disagreed with Laplace about how the solar system formed, and he thought that the planets were birthed from the sun due to a near collision with a passing star, giving birth to a conspiracy theory that still exists in small pockets today. James was a strange one. Rayleigh and Jean approached Wien's work and attempted to make it work for low frequencies. Wien's displacement law had simply said that the spectral radiance peaks at the wavelength given by the equation peak wavelength equals Wien's constant over the body's temperature. From this, Wien formed his distribution law, or approximation, which states that there is a certain amount of energy of a specific nature emitted at a particular wavelength, and that the peak wavelength depends on the temperature. Wien created this in order to try to tie together electromagnetic radiation, temperature, and energy, and by having a simple way to find the energy of a black body given by the radiation coming from the surface temperature of the object. However, despite being quite good at approximating short wavelengths or high-frequency radiation emissions, like visible light, it failed to accurately describe long wavelengths or low-frequency radiation emissions, like radio waves. If the low frequencies could be solved accurately, we would be able to research the entire electromagnetic spectrum. Rayleigh, along with Sir James Jean, tried to find a way to make the long wavelengths work to complete Wien's work. The Rayleigh-Jean law states that as the frequency of the radiation approached infinity, the energy output also tends to infinity. Or flipping it, that a wavelength that approaches zero wave displacement has an energy that approaches infinity. This new formulation worked for long wavelengths or low frequencies, unlike Wien's work. However, it instantly fails to get accurate results by the time it reaches microwaves. By the time it approaches ultraviolet light, it is off the chart. This became known as the ultraviolet catastrophe 11 years after the law was formulated, and by that point we already had Planck's solution. Both Wien's curve and Rayleigh-Jean's curve failed because of a specific reason, which had to do with the specific wave nature of light. We were trying to study matter, but we found that one of the best ways to study matter was to set it on fire and look at its light. The light would tell you what it is made of. But the issue is that a black body like our sun has its peak wavelength at green, but that it just means more radiation is in the green region. There are still going to be different energy levels with less particles than the peak, but they are going to be there. And a wave at the classical level is continuous. You can divide it infinitely, and you will always find another divisible value. So therefore, there is an infinite amount of energy levels, and therefore an infinite amount of energy. And that can't be true. The amount of particles at those levels will have less than the peak amount of particles, but there will still be an infinite amount, despite being less numerous per group. The Rayleigh-Jean law had stated that the intensity of radiation is proportional to the black body's temperature, and is also proportional to the fourth power of the wavelength. And starting with long wavelengths or low frequencies, the amount of energy output was finite and accurate. For example, according to Rayleigh's original paper, the spectral radiance observations matched that of potassium chloride when burned, which burns around 1000 degrees absolute, with a wavelength of 60 microns. But by the time the wavelengths needed to be ultraviolet in size, the amount of energy output would have to be infinite, which makes no sense, as even the sun would then have to have infinite energy, and we wouldn't be here due to that intensity. Rayleigh and Jean never actually proposed the ultraviolet catastrophe or anything of the sort, except that Rayleigh wrote, quote, "Speculation upon this subject is hampered by the difficulties which attend the Boltzmann-Maxwell doctrine of the partition of energy. According to this doctrine, every mode of vibration should be alike favored. And although for some reason not yet explained, the doctrine fails in general. It seems possible that it may apply to the graver modes." From this he provides an example of taking one-dimensional vibrating string and making it a three-dimensional vibrating sphere, and applies Boltzmann-Maxwell law to the radiation, and gets his famous wavelength to the fourth power law, which is a part of the Rayleigh-Jean law. And he concludes, quote, "Whether this equation represents the facts of observation as well as Wien's law, I am not in a position to say. It is to be hoped that the question may soon receive an answer at the hands of the distinguished experimenters who have been occupied with this subject. In 1900, Max Planck publishes his laws, which was to fix Wien's law. Rayleigh and Jean had also published their work in 1900, so Planck would not have seen that Rayleigh was hoping for this question to be answered until after he had completed his law, accidentally solving their problem at the same time as Wien's. Planck's solution was simple. A black body can be thought of like a box with a pinhole in it, and the only radiation that leaves the hole is from the thermal energy of the box itself. The box does not reflect or transmit any of the light that falls into the hole. The previous scientists were assuming that light waves bounce around the box and transfer their energy to the box and each other over time, and that light energy was doing so in continuous fashion, such that one photon of energy units might lose 0.001 energy units per bounce, or 0.0001 or 0.000001, and so there would be waves of light in the box at every wavelength, which there could be an infinite amount of, and so that breaks everything. But what if energy was quantized, such that a light wave could only become smaller if it matched a certain size, and that you cannot have an infinite amount of levels of energies, only discrete levels of energy, such that by the time the wavelength or frequency reaches ultraviolet, you don't have infinite amount, but maybe just a handful. Just set the energy E equal to the minimum energy level H, and multiply that by a natural number unit rather than a real number unit. Planck's law worked, but Planck thought the idea of making energies into discrete functions was just math. Albert Einstein showed why it was a fact of reality. The photoelectric effect showed that a quanta of ultraviolet radiation was able to cause an electron to be displaced from its metal plate. And in the reverse, Einstein showed that the photon was quantized, because it is the energy of the electron changing orbitals. An excited electron, when it de-excites, fires off a photon of that specific amount of energy difference. Einstein goes on to show that atoms really do exist, and that kinetic motion and temperature are related through this atomic photonic interaction of quantized energy exchange. 2 years after Einstein's miracle year, it is possible to provide a very simple example of what that atom is doing with the electron, and what the electron is doing with the photon, using Ernest Rutherford's brand new planetary model of the atom, which Niels Bohr improves upon in 1913 by showing the electron in the top orbital fall down and release a photon, which corresponds to that energy gap amount. And to pop it back up, you need to add that energy amount. This is how glow-in-the-dark stuff works. The light charges the electrons to the higher orbital, and then you turn off the lights, and as the electrons fall back to normal, they release light, and thus glowing in the dark. This is the birth of quantum physics, as we now have atoms which are moving electrons to different discrete energy levels, which are caused by, and cause themselves, the creation and annihilation of photons of those exact discrete energy levels. That physical exchange of energy is fundamentally reducible to a smallest quantity of energy. Hence, we can focus on looking at finding the building blocks that the Greeks were looking for. Finally, having the knowledge and technology to find that one in the many.
This video is possible thanks to contributions to the Existence University Patreon by viewers like you. Thank you.